section 2.6 talks about limits involving infinity. And we're going to do it starting with this graph. So let's look at a couple different limits, starting with number A, the limit as x approaches infinity of g of x. So that's this graph here. And what you have to do in your mind's eye is try and envision where the graph is going as you go out along the x-axis. As you go out towards positive infinity, where are you going in the y direction? What's happening to the graph? What y value is that getting close to? This is the part where you make me look good. What y value is this graph kind of settling down around as you approach positive infinity?
1.
Looks like 2 to me.
I think that's 1, so that would be 2 on this scale.
Oh.
That's all right. I appreciate you helping out. So yeah, as x approaches infinity, y approaches, or the limit approaches 2. So for part A, limit as x approaches infinity of g of x is 2. How about as we approach negative infinity? Does that change things up when we approach negative infinity? Do we have the same limit? Is it going to 2?
No, it's going to -1.
Yeah, good deal. So the limit as x approaches negative infinity of g of x is -1. What other limits involving infinity can we see with this graph? Let's take a look. Part C, limit as x approaches 0 of g of x. Now that one's kind of interesting. So for C, limit as x approaches 0 of g of x. Now let's see if you've been picking up on one of the big things about limits. If this limit exists, what two things have to be true? Or what two things have to equal each other?
Would it be the limit from the left and the right?
Yeah, well done. Thank you, Alejandra. So that means that the limit from the left, that is the negative side of 0 of g of x, has to equal the limit from the right of g of x. Those two things have to equal. Well, do they? Do they equal? Let's take a look. As x approaches 0 from the left, so that as we're getting closer to this point, but from the left, where's the graph going? Where's that y value going?
To negative infinity.
Negative infinity. Yeah, excellent. And as we approach from the right, where's that y value going?
Negative infinity.
Negative infinity. Negative infinity in both cases. So negative infinity and negative infinity. So they, in fact, they do equal, which is good. Now, if those two exist and equal, then what's that say about the limit overall?
It approaches negative infinity.
It approaches negative infinity. So that one is negative infinity. Nice. Good job. Let's try some more. The limit as x approaches 2 from the left. Okay, so let me put a little spot on x equal 2. That's right here on our graph. If you approach x equal 2 from the left, where's the limit going?
Positive infinity.
You got to be careful. From the left would mean the negative side of things. So
It's like negative infinity.
this way, towards that, when you're approaching from the left. So yeah, I'm going with negative infinity because the graph is going down here, but I appreciate your participation. Thank you. So the limit as x approaches 2 from the left of g of x is negative infinity. And then they flip things around in the next problem. Now they ask for the limit as x approaches 2 from the positive side. So that's e limit as x approaches 2 from the right of g of x. What's that limit as you're approaching from the right?
Positive.
Positive infinity.
Yeah, that one's positive infinity. Now I'm kind of surprised that there's not really a part F here. These two problems set up what I would think would be a nice part F. Limit as x approaches 2 of g of x. But maybe we can finish that one on our own. What would you say about that one?
Doesn't exist.
Yeah, doesn't exist. DNE is how WebAssign wants you to answer those. Does not exist. Cool. Now let's look back at these first two limits. So this one here and this one here. When you have some kind of a limit here, as x approaches infinity or x approaches negative infinity, these are going to be called horizontal asymptotes. That is, your line's getting closer and closer to that particular value of y. So it's a horizontal asymptote. This is another horizontal asymptote. Now let me make something really easy for you on one of the homework questions. When you're looking at a graph, the number of horizontal asymptotes you have can be 0, 1, or 2. So it's just going to kind of depend on how lucky you get, but it's going to be one of these numbers, 0, 1, or 2. Come on. Wanted to make that bigger for you, but I guess we're out of luck. So the number of horizontal asymptotes, you see them here. We've got one down here at -1. You got another one up here at 2. But sometimes those two are the same. Sometimes you have one horizontal asymptote. Oftentimes you don't have a horizontal asymptote at all. So the number of horizontal asymptotes you can get would be 0, 1, or 2. Now this graph has some other asymptotes as well. You can see a couple of vertical asymptotes, one at 0, one at 2. So there's no limit to the number of asymptotes you have, but there is a limit to the number of horizontal asymptotes that you can have. Now, how about finding these things? Well, there's some help in finding these things. We don't always have to necessarily look at a graph and hem and haw and try and figure out what's going on here. The handout that I put in the chat talks about these rules. This is stuff that you might have seen in college algebra. But basically, it helps you predict, in the case of a rational function, what's going to happen in terms of horizontal asymptotes. So there's 3 cases, and really 2 that we're going to worry about. Now I'm assuming that you've got a polynomial in the numerator and some kind of a polynomial in the denominator. If the degree of the numerator, and that's what's going on here, the degree of the numerator is less than the degree of the denominator, then you get y equals 0 as your horizontal asymptote. If those 2 degrees are equal, that is, the degree of the numerator equals the degree of the denominator, then your horizontal asymptote is just going to be the ratio of the leading coefficients. So let's do a couple examples that highlight both of these. And actually, I do want to be back here. Now for all of these, I'm assuming that we have a rational function that is P of X over Q of X is a polynomial in the numerator and a polynomial in the denominator. We'll start with a friendly one. And I guess I'll just keep on numbering. I'll call this example G. The limit as X approaches infinity of 8x squared minus 3 over 7x squared plus x minus 3. Now there's a couple ways you can do this. There's actually a lot of ways you can do this. Of course, you could look at the graph, you could look at a table, etc. But the thing that should catch your eye is that both of these exponents are the same. You have the same degree in the numerator and the same degree in the denominator. Both of these are polynomials of degree 2. So if that's the case, then the limit is just going to be the ratio of the leading coefficients. It's just going to be 8 over 7. That's all there is to that one. It's kind of nice. Let me show you why that works, though. And to actually prove this, what we'll do is this: 8x squared minus 3 over 7x squared plus x minus 3. So hopefully I've taken away the suspense, and now you can sit back and enjoy the show a little bit. You're going to divide by the highest power term in the denominator. So I'm going to divide everything here by x squared. And I have to do that in the numerator and denominator. I have to do it in both of them. So effectively, you're multiplying by 1 if you multiply by 1 over x squared divided by 1 over x squared, or if you're just dividing everything by x squared. How does that change things up? That's going to give me, well, 8x squared divided by x squared gives me 8. So it's going to be the limit as x approaches infinity of 8 minus 3 over x squared, and then 7 plus x over x squared is going to give me 1 over x minus 3 over x squared. Doesn't look a whole lot nicer, does it? But there's good news coming up, and it's going to take advantage of some of the properties of limits. The properties of limits allow us to do a lot of helpful things here to evaluate this. And some of the problems in WebAssign, you actually need to go through and put in some of these steps. So it's a good thing to pay attention to so that you can do this when you're doing your homework. Let me continue up here. So what I'm going to do is I'm going to take the limit of the numerator and the limit of the denominator. So I'm going to sort of spread out that limit. It's going to be the limit as x approaches infinity of 8 minus 3 over x squared divided by the limit as x approaches infinity of 7 plus 1 over x minus 3 over x squared. And now I can go even further. I can take the limit of this minus the limit of this. Let's do that without writing. Let's just look at that first part. The limit as x approaches infinity of 8. Well, 8 doesn't change. So as x goes to infinity or not, this is still going to be 8. But what's going to happen here when x goes to infinity? You're going to have 3 over x squared. So if x is 10, that's going to be 3 over 100. Or if x is 100, that's going to be 3 over 10,000. X is 1,000. Now that's 3 over 1,000,000. As the values of X get really, really large, what's going to happen to that term? Where's it going to go?
It's gonna be close to 0.
Yeah, that one's going to 0. So yay. In the numerator, we get 8 minus 0. How about in the denominator? What's the limit of the first one?
7.
7. Thanks, Jed. 7 plus
0.
0. Good. So that one's going to go to 0. And then one more. This one is going to go to 0. So overall, you're just left with 8 over 7.
Can you explain why it's 0 again?
Sure. Just take a look and think about what's going to happen if you start putting in some really, really large numbers. So let's focus on this part. Limit as x approaches infinity of 1 over x. Start imagining putting in some really, really large numbers in for x. 1,000, 1,000,000, 1,000,000,000, the national debt. You know, this number, this ratio is going to get really, really small, right? So you can kind of see it. Let me show it to you here. We'll put in 1 divided by x. And we'll do a little table. We'll put in 100 and then 1,000 and then 1,000,000, 1e6. So these numbers are getting really, really small. In fact, they're getting small enough that your calculator would have to start using scientific notation. 1e negative 6 means there's 5 zeros and then the number 1. So it's getting really, really small. Eventually it gets close to 0, and in the limit it gets to 0.
Okay, thank you.
Yeah, you could also see that on the graph. If you looked at it on the graph, and I don't know, does anyone have any idea where we could go to see that? Oh yeah, maybe Desmos. There we go. Take a look. As x approaches infinity, kind of ride this roller coaster all the way. As x approaches infinity, that line is getting really, really flat. It's getting closer and closer to 0. And you'd have to zoom in a lot in the y direction to see any daylight between your graph and the x-axis. I mean, those are just really, really small values. No two ways about it. So yeah, thanks for the question. Anything else on this one? So unless I'm asking you to show the work on these, I'm not sure I really see the benefit. Then hopefully you just say, oh, hey, this is a nice one. It's just the leading coefficients, right? There's the 8 and the 7. And it's the leading coefficients because the degree in the numerator and the degree in the denominator are the same. Now, if the degree in the numerator is greater than the degree in the denominator, then limit's just infinity. So you can play that game that we just played, but this time you're not going to get a lot of nice terms that cancel each other out like they did with the last one. This time it's going to go to infinity. Now there's a couple more cases that I want to look at. In particular, I think I might substitute a harder one for this. I don't know. Yeah, we'll do this one. If you weren't sure about this, what else do you think you could do to double check yourself? There's 2 things you could do, really 3 things, but 2 things that I would think of. One would be looking at a table and the other one would be looking at the graph. The graph and the table should both show you that this is going to positive infinity. So I think
Can you
one
use long
example.
division on that since they're the same degree?
So what you would do on that one, and since you asked, let me maybe take the chance and take a moment and just do it all out. Limit as x approaches infinity of x to the fourth minus 3x squared plus x over x cubed minus x plus 7. What I would do with that one is the same thing I did with the last one, which is divide everything through by the highest power term in the denominator. So in this case, that's your x cubed. So let's see what happens if I divide everything by x cubed, which is really like multiplying by 1 over x cubed and 1 over x cubed. That's effectively 1, but instead of canceling these out, I'm going to distribute these and divide each of these terms by that x cubed. And I'll show you maybe one more step than I did with the last one. It's the limit as x approaches infinity of x to the fourth over x cubed minus 3x squared over x cubed plus x over x cubed over x cubed minus x over x cubed plus 7 over x cubed. So I don't know if you need to show this step for yourself. A lot of you could probably just do this in your head and say, okay, if I'm dividing everything by x cubed like this, then in the numerator, I'll get x minus 3 over x plus 1 over x squared divided by 1 minus 1 over x squared plus 7 over x cubed. So let's take a look at each of these then. Each of these has a limit. We'll start in the denominator. In the denominator, the limit as x approaches infinity of 1 is 1. How about this one? As x approaches infinity, what happens to 1 over x squared?
0. Will it go to 0?
Yep, it's going to go to 0. So this is minus 0. And then over here, 7 over x cubed, that's going to get to 0 even faster. So a plus a 0 there. Then what else? Let's work up here. That one goes to 0. So it'd be a plus, can't see the yellow too well on this. Let me just do it here. Plus 0. How about this one? What's going to happen to this term as x approaches infinity?
0.
0. But here's the killer right here. This isn't going to 0, is it? You still got that x. And what's the limit as x approaches infinity of x? It's infinity. So yeah, that one's not going to 0. That one's going to infinity divided by 1 is infinity. So because the degree here wasn't bigger than or at least equal to this one, we couldn't get things to cancel out so that we get a finite limit. That one's going to infinity. Does that one help out?
Yeah.
Yeah, that was helpful.
Okay, thank you. Appreciate that. If you guys have some concerns along the way, say, well, wait a minute, I don't get this. I mean, hey, get some help, please. That's why they pay me the big bucks. So if something goes a little too quickly or you're a little bit befuddled, then reach out. Especially when we're not face to face, I can't see you. I don't know how well you're confused or how well you're understanding it. I mean, a lot of times I can read faces, but it's really hard in an online environment. So do yourself and your friends a favor.
So for the exams, we don't have to show all that work, correct? We could just say it's
Not on
infinity.
these. Not on these.
Okay.
I mean, those are kind of pretty standard. But let me show you one where I would kind of like to see some work. And that would be something like this one. Limit as x approaches infinity of the square root of x plus 3x squared over 7x minus 1. And that's a 7, my bad. 7. Now with these, what you have to do first is you have to factor out that term from the root. And I'm going to factor out the largest power term underneath the radical. So it's going to be the limit as x approaches infinity of the square root of x squared. Let's just do this in our heads. If I divide this term by x squared, or if I factor out the x squared, what's going to be left there? A 3. And then if I do the same thing here, if I divide this by x squared, I'll have x over x squared, but that simplifies to 1 over x. Now the denominator stayed the same, like that.
Would it be easier to start by taking it out of the square root? I'm just taking this at it.
Well, it's a good question. The reason I'm kind of taking my time here is because after we do this, I'm going to repeat this one with the limit as x approaches negative infinity of this same problem. And so I actually kind of want to start right there.
Could you just could you take out root x, or do you have to do the root x squared?
Well, there's a little nuance about factoring out the x squared like this. Now, when x is approaching positive infinity, it works out pretty nice. You're just going to get the limit as x approaches infinity of x times the square root of 1 over x plus 3 over 7x minus 1. So that works out nice. And at this point, you can see that the degree in the numerator and the degree in the denominator match. So if I play my little game of dividing everything through by the highest power term in the denominator, then I'm going to divide everything through by x. And that'll give me, well, this is going to cancel here, and that'll cancel there. So I'll get the limit as x approaches infinity, square root of 1 over x plus 3 over 7 minus 1 over x. And all is well and good. The lion and lamb are best friends. Hey, looking good. Let's think about this limit. You can actually take this inside this square root. The limit as x approaches infinity of 1 over x plus 3. What's going to happen to the 1 over x term?
0.
0.
No.
What happens to the 3 term as x goes to infinity? That's
Still
just
3.
3. How about in the denominator? What's this limit in the denominator?
7.
7 minus 0. So overall, you get the square root of 3 over 7. Are we good on that one? That'd be the answer for this problem.
Yeah.
But I said I wanted to revisit this one and look at what happens as we approach negative infinity. And I'm just going to start out from this step right here, where we factor this out. Now, this is where you got to be careful. And this is where some people are going to get this one wrong, because there's really two different possibilities here when you take the square root like this. There's the positive square root and there's the negative square root. So which one do you take? Well, if you're approaching positive infinity, then the values of x have to be positive. So it makes sense to take the positive root. But if you're approaching negative infinity, we're going to take the negative root. And let me just try and be clear about what's happening here before I show that. If you take and square 5 and then take the square root, you get the square root of 25, you get 5. If I take negative 5 and square it, I get 25, square root is positive 5. So if you're starting out with an x squared term and then taking the square root, which one should you get? Should you get the 5 that you started with or the negative 5? And which one of these is the correct answer when you take the square root of 25? Technically, there's two possible answers. When you take the square root of 25, it's plus or minus 5. When you're going towards negative infinity, you want to take that negative root. So this is going to be the limit as x approaches negative infinity of negative x times the square root of 1 plus x, 1 over x plus 3 divided by 7x minus 1. So notice you've got a different sign here because you're simplifying this root and going towards negative infinity. Let's play our game now that we've been playing with the last several problems. I'm going to multiply by 1 over x. And this is going to simplify kind of like the previous one did, with one exception. That one exception is I've got a negative here. So it's going to be negative the square root of 1 over x plus 3 over 7 minus 1 over x. The rest of this should be looking familiar. That limit turns into negative the square root of 0 plus 3 over 7 minus 0, or negative square root of 3 over 7. So by going to negative infinity, you had to take account of that negative limit. It's not something you'd have to worry about if you were going towards positive infinity. But I know there's at least 2 problems like this in the homework. Another one of them has something like, I don't know, square root of 1 plus 4x to the 6th. And you would simplify that by factoring out the x to the 6th. That leaves behind 1 over x to the 6th plus 4. You'd have to take plus or minus out of this, depending on if you're going to positive infinity or negative infinity. But just be advised, have a heads up that that's what's going to go on with that one. Let's look at the graph and see a couple things about these.
I have a question real quick.
Yeah, please, Marley.
How do we know like what term to multiply the numerator and the denominator by? Like you did 1 over x.
It's a great question. You're always going to look for the highest degree term in the denominator. So that's been consistent with all these problems that I've done so far. Highest degree term here is an x. Highest degree term with the previous one was an x cubed. Even though I had an x to the 4th here, I went with x cubed. The one above that one, I used an x squared, right? Because the highest degree term in the denominator was an x squared. So it's always the highest degree term in the denominator that you're going to use to divide and try and simplify this a little bit further. Is that what you're looking for, Marley?
Yes, thank you.
Excellent.
I have a
Appreciate the question. Yeah, go ahead.
And so you would do 1 over the highest like value in the denominator, 1 over that, not just, is that
Yeah,
what you meant?
so I was just showing the factorization of this. There's a problem in the book, something to the effect of 1 plus 4x to the 6 over, say, 2 minus x cubed. And if you're looking at that limit, then you'd have to play around with this, factor out effectively an x cubed, and then to finish this up, you divide everything by the highest power term in the denominator, which also happens to be your x cubed. So, you know, I'm getting some questions on this, so maybe I should just like do this one. Let's just kind of crank this out rather than leave you hanging. Maybe it'll reinforce things a little bit and help you out. So limit as x approaches negative infinity of the square root of 1 plus 4x to the 6 over 2 minus x cubed. And let's get that in view. As I did with the previous one, I'm going to factor out the highest power from this radical, which is an x to the 6. So I'll have the square root of x to the 6. When I factor that out, it's going to be 1 over x to the 6 plus 4. If you distribute this, you should see that you get this here. I kind of left myself short on room here. Limit as x approaches negative infinity. Square root of x to the 6 is going to be an x to the third term. But because we're going towards negative infinity, you want to choose the negative root here. So choose the negative root. So it's going to be the limit as x approaches negative infinity of negative x cubed square root of 1 over x to the 6 plus 4, 2 minus x cubed. All right, Marley, what power term should I divide everything by?
X cubed.
Yeah, so I'm going to multiply by 1 over x cubed and 1 over x cubed. The nice thing is that those two are going to cancel. So that's just going to leave me with limit as x approaches negative infinity of the square root of 1 over x to the 6 plus 4 over 2 divided by x cubed minus 1. Now we can start taking the limits kind of piece by piece. I can take this whole limit underneath the radical and take a look at the limit as x approaches negative infinity of 1 over x to the 6. Now, does it matter that I'm going towards negative infinity or positive infinity? No. This is still going to end up being 0. So it's going to be square root of 0 plus what?
Do we need the negative sign in front of that?
No. Let's see. Yeah, I did lose the negative sign. Thank you. So I need that negative up there.
Are we supposed to square that 4 to make it 2?
Well, we're going to take the square root of it
Yeah.
eventually. Yes.
Okay.
And so this would be 0 minus 1. And the negatives are actually going to cancel each other out, right? So I'll have -2 over -1. So I have a limit of 2. And that's your limit. Let's understand a little something more about that graph, or what the graph of this function would be. And that is what this means about the graph when I graph it. The limit as x approaches -infinity is 2, means that, you know, at some point, my function is going to get close to the graph of y equals 2, 1 and 2, as I go out towards -infinity. But how would this change if I went towards positive infinity? Well, the only difference if I went to positive infinity is that this would be a positive x cubed instead of a negative x cubed. I would have taken the positive root here instead of the negative root. And that means this would be positive here. And if that was positive, this would be negative. So my function would be going towards -infinity. And basically what this is saying is that you've got 2 different horizontal asymptotes. One at -2, one at +2. One as you go out towards positive infinity, one as you go out towards -infinity. And let's see that by looking at the graph. So that's this one here. Let me see if I can't make that a little bit easier to see. There you go. So kind of an unusual behavior here. I don't think I would have suspected something like that. This little kind of cup or bucket shape actually looks like the Big Dipper, at least a little bit. Then eventually the graph settles down and gets close to, but it never quite touch +2. And on the other hand, as you go out towards positive infinity, the graph's getting closer to, but never quite touching -2. By the way, the graph can cross your horizontal asymptotes. In fact, this one does. So if I were to put in the graph of y equals -2, the graph actually does cross this horizontal asymptote. It's not a big deal. Some people think that, oh, they can't ever touch. Sometimes they do, sometimes they cross it infinitely often. But eventually it gets close to that point. All right, I hope that extra example helped. So,
I have
Yeah.
a question.
go ahead, Chloe,
Um,
please.
It's just like for when you're doing the work, every single time you do a step, do you have to write limit, like going towards -infinity, or just like the limit part before every time you do a step?
Only if you want to keep your instructor happy.
Okay.
Yeah, no, and to be more accurate and fair to your point, yes, you do, because a lot of
Okay.
these things, and I deeply appreciate it, because a lot of people get lazy. They write limit the first time and they don't write it the rest of the way. But a lot of what we've written here only would hold true if you're taking the limit. Okay,
Yeah.
this equals this only because I'm taking the limit. If I didn't have this here, this would not equal this. It just doesn't. It's only
Okay.
because I'm taking the limit that this stuff is true. So yeah, I do get kind of unhappy, and I have to wrestle with myself as to whether or not I should be taking off points if you leave off the limit in between these things. So what it comes down to is, have my favorite sports teams been winning over the weekend? If they, maybe I'll let it slide. If not, then maybe we're gonna lose a point. But if you
Okay.
don't bets, then I'd put them there for me, please. Yeah. So thank you so much, Chloe. That's a great point.
Yeah.
I struggle with this a lot, and at least you've been forewarned. All right. Anything else on this one?
I was wondering if we're going to be concerned with oblique asymptotes.
Not so much. Not so
Okay.
much. You do get them when the numerator degree is one more than the denominator degree. Somebody mentioned long division. That's what you'd have to do here. And what you do is you'll get a quotient and a remainder. And the quotient, so it's right up here, y equals the quotient would actually be your oblique asymptote. So I don't think I want to do the long division for this one down here, but it would involve an x, y equals x plus or minus some number. And that would be your oblique asymptote in that one. But no, we're not going to go to that extent here. It's a good question, though. Appreciate it.
Thank you.
So these limits towards positive and negative infinity, those are your horizontal asymptotes. Let's see if we can't do two more. Sticking with the kind of the theme here of simplifying these things. Let's look at this one in the bottom left. So I've lost track of where we're at, what example. So I'll just call it example J. Limit as x approaches infinity of 7 minus e to the x over 7 plus 3e to the x. And even though it's not quite a rational function like a polynomial, we can still treat it with the same techniques that we did with our rational polynomials. I want to divide by the highest degree term in the denominator, and in this case, it's just e to the x. So let me divide everything through by e to the x. And the reason I'm showing this part right here is to kind of emphasize that we're not changing the value of the fraction. This term that I have here in green parentheses is something divided by itself. And something divided by itself is 1. So I'm multiplying by 1. It's not going to change the value of my expression. If I distribute this stuff, it is going to rearrange things, and that's okay. It's still going to have the same value. But in rearranging things, I'll better be able to see the limit. I'll have 7 over e to the x minus 1 over 7 over e to the x plus 3. See if you can't fill in the limit. What's that limit going to be? Throw your answer in the chat. All right. Got a few answers here right away. Thank you, and thank you. There's another one. Thank you, looking good. AC, looking good. Lexus, Omar, all right. Good. I appreciate knowing that everyone's with me on this one. So if you look at it piece by piece, then as x goes to infinity, this is going to a big fat 0. Minus 1 over 0 plus 3. And the result of that is the quotient negative 1/3. Yay, well done. Now, one last one here to kind of wrap things up with asymptotes, and that would be this one down here. There we go. So we'll call this one example I. y equals 2 plus x to the fourth over x squared minus x to the fourth. If you're looking for the horizontal asymptotes, like you are in this one, then one of the things you're gonna have to find is the limit as x approaches infinity and the limit as x approaches negative infinity. So let's take a look at both of those. So for our horizontal asymptotes, I want to look at the limit as x approaches infinity of 2 plus x to the fourth over x squared minus x to the fourth. Let's see if we can't do this a little bit faster than we've done a lot of our previous ones. This one's a very nice case of working with asymptotes. Can someone tell me why? What's nice about this case?
The degrees are the same.
Yeah, the degrees are the same. Perfect. You have a degree 4 and a degree 4. So this turns out that the limit is just a ratio of these leading coefficients. So the leading coefficient here in the numerator is the coefficient of the highest degree term. It's not the 2 here because that's out in front. It's the 1 because that's the coefficient of the highest degree term. That's a 1. That's a -1. And you're done. Now, it's not really going to matter if you're going to positive infinity or negative infinity, because when you have a negative number to an even power, it cancels out. So that's really going to be your one and only horizontal asymptote. So y equals -1 is the horizontal asymptote. What about the vertical asymptotes? Vertical asymptotes. That's going to be where the denominator equals 0, which is x squared minus x to the fourth equals 0. Now, I hope you don't have to go to Google to figure this one out. For this one, I would start by factoring out an x squared, which leaves behind 1 minus x squared. And then it factors even further. It factors as x squared times 1 minus x times 1 plus x equals 0. And you should be able to read off the factors of this. What are the factors? Or excuse me, what are the roots, I should say?
0, 1, and -1.
Bingo. 0, 1, and -1. So those are your vertical asymptotes. So we've got 3 vertical asymptotes and 1 horizontal asymptote. When you look at the graph, you should see this. So let's take a quick look at the graph to make sure that it matches our expectations. I thought I had this one programmed in. Maybe not. All right, give me a second here. So obviously you can graph this on your graphing calculator. I'm choosing to do it on Desmos. But to get it in, you highlight this term in the numerator, then you hit the division key or the /, and divide by x squared minus 4, or x to the fourth, squared minus x to the fourth. So you can see several things here. You can see your vertical asymptote. You've got 1 at 0. You've got a horizontal asymptote at -1. And let me see if I can't change this scale a little bit. You can bring in, there should be, yeah, there it is. Not very easy to spot, but there's the rest of the function up there. And you've got two other vertical asymptotes. You've got one at -1 and one at +1. So you can graph all of those if you'd like. X = 1, X = -1, and Y = -1. Maybe you want to make those different colors. Red, because it's not going to touch it. Okay, there you go. There's your graph. But it's a nice validation of the work that we've done. And actually, I could probably put in X = 0 because that's also a vertical asymptote. Any other thoughts or comments on this one?
I've got a question about limits themselves. When you're writing out the work, should I be using that fancy L or just regular?
That's
L?
my L. Yeah,
Okay.
You don't have to use a fancy L.
I wasn't sure if that was a special calculus symbol there or not.
It's just mine. Speaking of special calculus symbols, you might notice that when I write sections, like section 2.6, what we just covered, that I use a kind of elongated S. Unlike my limit, that is actually a special mathematical symbol, but we won't learn that until chapter 5. So I've been playing a joke on you every time I write down a section number, because that is a symbol that we will use. So yeah, but thanks for asking. That's cool. Anything else? All right, I think it's break time.